value decomposition is a fundamental matrix factorization technique in linear algebra. It is a matrix factorization technique. It is widely used in data science, machine learning, and signal processing. So, unique decomposition of any matrix into orthogonal components. So, we have a matrix. We will divide that matrix into orthogonal components. The advantage of this SVD is it facilitates efficient computation in data analysis, also dimensionality reduction, noise filtering, data compression, etc. How SVD is computed? First of all, we have to compute A transpose A. This matrix is symmetric and positive semi-definite. Its eigenvalues are orthonormal and give right singular vector V. Its eigenvalues lambda I are non-negative. So first compute A transpose A. Then extract the singular values sigma I. Singular value equal to root of lambda I. They are square root of eigenvalue of A transpose A or A transpose. So after extracting singular values, you have to compute U, that is left singular vectors. Once V and sigma I are known, we get Ui equal to 1 by sigma I AVI. This ensures columns of U are orthonormal. So definition of SVD, let M by N matrix A, SVD decomposes into three matrices U, sigma, V. So A equal to U, sigma, V transpose. U is a M by M orthogonal matrix. It is a left singular vector. Sigma is a M by N diagonal matrix with singular values. V transpose is a N by N orthogonal matrix or right singular vectors. So how to compute this? First of all, you have to find U, sigma, Vt, then find the product of these. So first form A transpose A. What is A transpose? A transpose means you have to interchange the rows and columns. That is, the rows here, these are the rows, 3, 1, so it becomes column. Second row becomes second column. This is the A transpose. So multiply A transpose into A. This into this matrix. So we need to find the eigenvalues. To find the eigenvalue, we have to take the determinant of A transpose A, that is this matrix, minus this 9, 3, 3, 5, minus lambda into, what is I? I means identity matrix, 0, 1, 1, 0. Sorry. And 0, 0. So this becomes, you have to find the determinant of 9 minus lambda into 1. 9 minus lambda, then 9, 3 minus lambda into 0. So this becomes 3. 3. So this becomes 3 and this becomes 5 minus lambda. So you have to find determinant of 9 minus lambda 3, 3, 5 minus lambda. So how to find the determinant? First you have to multiply these two. 9 minus lambda into 5 minus lambda minus this diagonal. It is 9. So removing the bracket, 9 into 5 minus lambda square minus 9 lambda minus 5 lambda. So this becomes lambda square, this is plus lambda square minus 14 lambda plus, here one minus is there. So 45, this is 45. 45 minus 9 is 36. So solving this, you will get 7 plus or minus root of 30. Then you have to find the singular values, that is lambda, root of lambda, it is root of 10.1, that is 3.2 and 1.8. Two sigma values, sigma 1 and sigma 2. Then for lambda 1, we have two lambdas. Now we have lambda 1 equal to 10.60555. Lambda 1 equal to 10.6555 and lambda 2 equal to 3.39445. Okay, now we need to take each lambda 1. For lambda 1, we need to find the eigenvectors. So, A transpose A minus lambda 1 into I, the whole into V1 equal to 0. So, what is A transpose? The whole A transpose A is 9335. So, that is 9335 minus lambda 1 is 10.6555. That into I value is 1001. So this is equal to 9335 into minus 10.6555 minus 10.6555. This is equal to, what is 9 minus 10.555? That is minus 1.60555. Then 3 minus 0, 3 plus 0, 3. Then 3 plus 0, 3. 5 minus 10, that is minus 5.60555. So we got this matrix. Okay, this matrix, we got this. That into V1. V1 means here we are having two singular values. So we need to put two variables in the column matrix. This is equal to 0. So for we need to solve this equation. Okay, how to solve this equation? So this will give minus 1.60555 x plus 3y equal to 0. From this you will get 3y equal to
1.60555 and y equal to 1.60555 divided by 3 this into x. So by solving this, you will get 0.53518. Now y equal to this value. So in order to get the value of y, take x equal to 1. X equal to 1 means we will get the eigenvector. Eigenvector in the form xy. Value of x is 1 and value of y is 0.53518. So we got the eigenvector. Now, next step is we need to normalize it. For normalization, you have to calculate the norm of V1. Norm of V1 means we have to take the square root of squares of all values present. 8 square. This is equal to 1.135. Now V1 equal to 1 by norm of V1 into V vector. V1 vector. That is norm of V1 is 1.135. Therefore, it is V1 equal to 1 by 1.135 into V vector is 1 and the next element is 53518. Solving this, you will get this value. Now consider that the property is that lambda 2 is orthogonal to V1. So we can write V2 like this. You can interchange these values and put a negative sign here. So we got V1 and V2. This is V1 and this is V2. So the V vector is, you can add both these one, 881.471 minus 0.471881. So V transpose is equal to 0.881 0.471, that is minus 0.47. This first row becomes first column and the second row becomes second column, that is 471.881. So we got V vector and V transpose. Now we need to build sigma. Sigma means you need to put all the singular values in descending order on the diagonal. This one is the diagonal. We are having two singular values. So first singular value is 1.842 and the other one is 3.256. So we are having two sigma values. Sigma 1 equal to 3.256 and the other sigma value is 1.842. So the other values are 0, 0. You need to put values in this diagonal. The higher values this one, so put here 256 and put 1.842 here. Now we need to compute U. How to compute U? That is AVI divided by sigma I. So AVI, what is A? A is already given. This is A, 3012. So 3012. This one is A vector. B1 is also calculated. This is B1, 0.881, 0.471. 0.881, 0.71. So you need to take the product. Okay, so this is 3 into 0.881 plus this into this plus this into this. 1 into, that is 3.114. Next is 0 into 0.88 plus 2 into 4.471, that is 0.942. So this is AV1 divided by sigma I, that is sigma 1. Normalize this using sigma 1. So we got AV1 like this, and we need to normalize this using sigma 1. So that is 1 divided by sigma 1 is 3.256. So 1 divided by 3.256 into AV1 into AV1. So 3.114942. So by simplifying, you will get matrix like this. Similarly, you have to find out the second column of U, that is AV2. A is this matrix. It is given in the question. And V2, we already found the V2 minus 0.881. This is V2. Multiplying this, ordinary multiplication, 3 into and 1 into this one. You will get this matrix. Now again normalizing, sigma 2 equal to 1.842. Normalizing this, you will get 1 by sigma 2 into AV2. So AV2 is this one. So 1 by sigma 2 is 1.4842 into this matrix. So simplifying this, you will get this one. Now we need to check the orthogonality. That is U1 into U2 is approximately equal to 0. Each norm of Ui equal to 1. If this is okay, you can write the U matrix. So first column of U matrix is this one. First column of U matrix is U1, and second column of this is U1, and this one is U2. This is U2, and this one is U1. U1 is this. So we got U matrix also. Then what is A? A matrix can be represented as the decomposition of U, sigma and Vt. So we already got U. This is U. And this one is sigma. And this one is V. V transpose. Don't forget to put the transpose. So once you multiplying these things, you will get A. So you can verify this using singular triplets AV1 equal to sigma 1 U1 and AV2 equal to sigma 2 U2. So in some cases, you need to get the rank 1 approximation. Rank 1 means you have to keep only one singular value. That is you have to keep the largest singular value. Rank 2 means you have to choose two singular values. You have to arrange. We had already put the singular values in diagonal values in singular values are sorted and placed in the diagonals. Since we are plotted in diagonals, we can choose the first two values if rank is 2. So A1 equal to sigma 1. Sigma 1 is 3.256. 3.256 is sigma 1, and U1, that is first vector alone. U1 is 0.971, 0.971289 into V1T. V1T means you have to choose. I will tell exactly. Look at this diagram. Look at this matrix. 3.256, that is sigma 1, that is this value, into U1 means the first column value. Then V1 means the first row value. Multiply this, you will get rank 1 approximation. Goal: any matrix A can be seen as rotate, structs, rotate. V is rotates the input feature space to specific independent direction. Sigma structures by some amount. Sigma 1, singular value of 1 is greater than or equal to singular value 2. U rotates into output space. Each triplet Ui, sigma I, Vi means if we feed direction Vi into A, it comes out Ui by scaled by sigma I. So we keep only top. Sigma gives best low rank approximation. This is one application. You just study SVD application as compression or denoising. This will give low rank approximation.